So when I graph the function f of x equals sine x, what I'm basically saying is that x is now the angle, okay? And the y-coordinate of that angle, and the y-coordinate on my graph is going to be the sine of that angle. Okay, so guys, when we did sine on the unit circle, how did we find, say, the sine of 0 on the unit circle? What did we do?
Look for the y-coordinate.
You go to 0 and write down the y-coordinate, right? So what is the y-coordinate at 0? 0. What's the y-coordinate at pi over 6 radians?
1/2.
1/2. Is everybody with me? What's the y-coordinate at pi over 4 radians?
Radical 3/2.
Are you sure?
Wait, radical 2/2.
Radical 2/2?
Skip a step.
What's the y-coordinate at pi over 3 radians?
Radical 3/2.
Are you guys with me? That all we're doing is traveling around that unit circle. All right. What about at pi over 2? One. And then what happens as soon as I get up to that 1, it just starts coming back down, right? So all of a sudden this will be square root 3/2, square root 2/2, 1/2, and then 0 again.
Is this the whole country thing?
Mm-hmm. Other side. You put it in there.
Do they go back up again?
You tell me, what's the y-coordinate at 7 pi over 6? Negative 1/2. And then at 5 pi over 4, it's negative square root 2/2. Is everybody with me? And then negative square root 3/2. And then negative 1/2. And then negative square root 3/2. And negative square root 2/2. And then negative 1/2. And then 0. And could I keep going around?
No.
Yeah, you could. I don't know the point though.
How are we feeling so far?
This is interesting.
I feel like you're doing the same thing on a different piece of paper.
Kind of. Not really. Because the difference now, if I look at what we have here, and I look at that and I say, well, my x-coordinate was that angle, so pi over 3. My y-coordinate is square root 3/2. I now have coordinate pairs I can graph of the function where I put in the angle and I get the sine of that angle out. Okay? So it's going to look a little bit different. Now, we are going to graph every single one of these coordinate pairs. It's going to involve decimals because the square root of 3/2 is not an easy point to graph. Okay, so like the 0 and the 1/2 are fine. Hey guys, can somebody with a calculator tell me what is square root 3/2?
0.866.
0.866. Okay, what about square root 2/2?
Wait, wouldn't the 1/2 be 0.5?
Do you know how to graph 1/2? The whole idea of the decimals is just to make it easier to graph. Okay? What's square root 2/2? And then we have 1, and then the 0.866, and the 0.707, and we have 1/2, and we have 0. Okay. And that's all we're going to do with those for now, okay? Okay, now, if I go to plot these points, now what I have to do is plot these coordinates on this graph. Okay, so if this is pi over 2 right here, what does that make this one?
Pi over 4.
Pi over 4. And as you guys look on your unit circle, do you see how pi over 3 and pi over 6 are close to pi over 4, just a little bit on each side of it? Do you guys see what I'm saying there? So I'm going to call this pi over 6 and this pi over 3. And likewise, this dash is 3 pi over 4. And so now these marks on the x-axis represent the different angles on the unit circle. Cool? So, my first point, 0, 0, is at 0, 0. That should not surprise you. Then life. Okay. And for right now, guys, let's go ahead and call the very top line 1. So each going up, each one counts as 0.25. Okay? So the next point I need to graph is the point pi over 6 1/2. So I'm going to go here to pi over 6, and then 1/2 would be right about here. That's what I was trying to go for. What's my next point? It's pi over 4, 0.707. Guys, the point I'm looking at, I'm doing this one. Now, to plot pi over 4 and then 0.7, pi over 4 is the line. 0.707 is going to be just short of that third line because it's not quite 0.75. Okay, so about 0.707 is right about here. Pi over 3 and 0.866 is going to be just about here. And then pi over 2, 1. How are we feeling so far?
No, it makes sense. I'm just confused on why we're doing it.
Sure. Because it's going to be a while. First, we got to see what happens, and then we can talk about why this happens can become useful. Okay?
I'm a little confused. I don't know, this is all overwhelming. I'm putting the points down, but I just don't understand. Like, part of it, I just don't know why, but, like, I'm not very good with fractions, so I don't understand how, like, can you zoom into the x-axis? Like, how is that 4 pi over 3 and 3 pi over 4? How is that 3 pi
Oh,
over
you're right.
4?
This is 2 pi over 3. This is 2 pi over 3. These are just the angles from the unit circle, bub.
Right,
as you're
but
going
how
up.
is 2 pi over 3 smaller than 3 pi over?
How is 2/3 small? You good? 2/3 is smaller than 3/4.
I just, why are those points going there? And why are, I don't know. Like, why is 2 pi over 3 going there? 'Cause
As
they're
opposed to where?
not- I don't know, just like why there?
So these are the angles on your unit circle, yes?
Yeah.
All right. Look here. This is smaller than this, yeah? So this is closer, like it's meant to be the same thing. So from here to here is equivalent from here to here.
Okay.
Which is why I don't have them directly in the middle. Like when you look.
Yeah.
Like it's meant to be that this distance is equivalent to that tiny distance on the unit circle of the angle. Now, guys, we're gonna do this down the side. The other side is gonna look almost identical, right? So now the 2 pi over 3 is gonna be over here. But it's at the same height, 0. And that's me taking these exact same numbers down this way. Now, what's gonna happen when I do the negatives? Like all of these ones are the exact same thing, only negative, yeah?
It's gonna be in a different quadrant.
It's just gonna keep going, like, it's gonna do this.
Yeah.
How are we feeling so far? If I were to ask you, what do you see here? Do you guys see how this graph starts to make this lovely kind of wave pattern?
Yes, I've seen these in memes about math.
You've seen them in memes?
Yes, about math.
I've seen them relating to circles.
Because they are circles, yeah. This is what comes about from going around a circle.
That's interesting and scary.
How do you have, like, I'm trying to put the points in, but how do I know where square root 2 and 2 is?
That's why we did the decimals.
Right, 0.7 and 7.
Yeah, so I have this one right here. If
It's on the scale of 1.
Mm-hmm.
You made everyone sad. They're not talking.
That's not good.
Is that for me?
No. Now, what's going to happen on the other side of the graph?
It's gonna follow that pattern.
It's gonna like flood, basically.
From here on out, we're going to focus on only a few coordinates on the unit circle. Is everybody with me? And you guys, we're going to focus on the easiest ones. What are the easiest coordinates on the unit circle, you guys?
0, 0.
0, 0 is not on the unit circle.
2 pi, pi over 2.
The pi over 2, like when I sketch, and I'm going to do a really rough sketch of this, okay? Here's my unit circle. Are you guys with me that this is a pretty easy point? Okay. What about this one? Mr. McCarthy's going to walk in here in 2 minutes.
What's he gonna talk about?
He's going to hand me something and ask me to read it.
Shouldn't you switch the 1 to 0?
You should read
Oh, yeah, thank you.
You should read out loud to the class.
No.
Is it teacher business?
It is graduation business.
Ooh, am I gonna graduate?
No,
Not this year.
not next year.
All right. So, guys, so if I want to figure out, so we're talking about sine, right? And these are the points that we just found on the unit circle. Can you see how they are the key boundary points for this wave-like motion of the graph, okay? So to come up with your graph of y equals the sine of x or y equals the cosine of x, there's a couple of things I'll expect. The easiest way for me to describe it is we have peaks and we have troughs of this wave, okay? And those come from going around the unit circle. And notice our y-coordinates, what happened is we went up, and then we came down, and then we kept going down, and then we started coming back up. And we could keep going around the circle, and this graph, it keeps going, and it just goes this way. Okay? Is everybody with me? All right, now, next what we want to do is to say, well, what would the sine of negative pi over 2 be? Well, what do we know about negative angles? They just travel in the other direction, yes?
Yeah.
So if I go to, positive pi over 2 goes up to the top, negative pi over 2 goes down. So what is the sine of negative pi over 2? Negative 1. And then if I keep going this way, I'm traveling negative, yes? When I get to negative pi, what's my sine? 0. And I go to negative 3 pi over 2, my sine becomes 1. And if I go all the way around to 2 pi, my sine becomes 0. How we doing? Now, when you guys draw your graphs, I expect to see curve.
Do we have to plot the points in between?
No.
Okay.
As long as I can tell that your graph is curved and that you know that it's curved, we can stick with just those those axis points. Okay? Now, what are some things you notice about this graph? Anything? Wavy. Okay. The fact that it's wavy gives it a really special name. I'm going to tell you the name. You do not need to know this name. We call it sinusoidal. But it's like one of those words I love because I feel so smart when I say something is sinusoidal. Okay? And essentially sinusoidal really just means wavy. What else do you notice?
It's consistent.
What do you mean by that?
It's just predictable because it goes up, other one, other goes down 2, other up 2, then down 1. But it really just go up.
But it continues forever, yeah?
Yeah, so it would just go up 2 and down 2 each time.
I don't like the phrase up 2 and down 2, but if I were to go say up and then down and then up and then down and then up, you with me? Okay. And in fact, wouldn't you say that means it kind of repeats itself? Are you guys comfortable with that? And why does it repeat itself? Because we just keep going around the circle. Okay? You know some other things that go up and go down and then go up and then go down and then go up and then go down? The amount of light coming off the moon? The tides? Yearly temperatures? Do you guys see what I'm saying here? So the reason we like sinusoidal functions is that there are a lot of real-world phenomena that repeat themselves over and over and over again. Miss Meister's distance from this building. Every day. I go home. My distance is far away. I come back. I go home. I come back. The amount of oxygen in your blood in this exact moment, every breath, upper oxygen levels and then down and up and then down. You guys, so why do we care about these? It's so that we can figure out models to help us understand all of how when we have repeating phenomena. Someone's hand was up.
Yeah. I was wondering, could your coffee be an example of that?
The amount of caffeine in my blood? Sure can.
Oh, I meant like if you drink it, like it could be for any drink, like goes down or something like refillable, like coffee. That.
Oh, sure, the level in it?
Yeah.
Sure. You know what else follows a sinusoidal pattern?
The like EKG machine at the hospital.
It's not, that one's not quite sinusoidal because it's like, it's not like smooth curves.
It's either
Okay.
beating or it's not.
Huh?
It's either your heart's either beating or it's not.
The amount of, what I was going to talk about was the overall temperament of a school building. This is true. Pay attention to this. How did you guys feel in February?
What happened to February again?
The world, everybody hates coming to school in February. Am I wrong? February's like the worst.
February? I can't remember that far back. I'm not kidding.
That was just
That's when you
after
were doing-
winter break and it's just like
You hit this kind of lull. So every year, people's attitudes towards school start out really high in the fall, and usually about October, we're all like a little cranky.
And then like Christmas break it goes up.
And then all of a sudden you're back to Christmas break. Everything's good. And then literally the February, March doldrums. And then it starts you go on spring break. It starts to get warm outside. People don't mind waking up in the morning.
Third quarter is the worst quarter. Like-
Fourth is.
Not third.
No, because now we're just in this dull period where nothing's actually happening and we don't even need to be here.
You have a third, like you have to do stuff and there's so much fun stuff.
I have your class is the only class where I have an actual paper.
That's because I'm a mean teacher. That makes you keep learning. Yeah.
Yeah, we should be watching movies right now.
Yeah, not happening. Okay.
What's their math movies?
So,
No, there's actually a movie about math. It was like that janitor kid who was like really smart.
there's several. Good Will Hunting. I'll never show it to you guys because the language in it is atrocious. It's a very good movie,
Can you go
but
some examples?
lots of bad language. The Imitation Game about Alan Turing, who was a code breaker for the Enigma machines during World War II. Real guy. He made the first supercomputer in order to break the codes. There's one called A Beautiful Mind about economist / mathematician. There's lots of hidden figures.
There's this one that's very vaguely related to math. It's called like The Scholar and the Psycho, where they're basically trying to make a dictionary.
Oh yeah, I've seen it.
Yeah, but they go about it very mathematically.
I haven't seen the movie. I saw the previews for it though.
We should watch that movie.
Or we're gonna do this now.
I tried, guys. I'm sorry.
Guys, the math word for a graph that repeats itself is that it is periodic. And so a periodic graph has what's called a period. The period of a graph is the time it takes to repeat itself. Okay. So, everybody see my cursor? Right here? I'm going to trace the graph, and I just need you to tell me when it's going to start repeating itself. Okay?
Now.
Now, yes? And then the next one will go like this. Okay. So that's the period of the graph is this distance, which was 2 pi. All right, now, every wave has something called an amplitude and a midline. So my midline cuts the waves in half. So in this case, that midline is the x-axis, or all the places where the y-coordinates are 0. Another way of thinking about that is the midline's your point of equilibrium.
See amplitude, how high and low it goes.
The amplitude is the distance from either the peak or the trough to that midline. So my amplitude is this distance.
That'd be 2.
It would not be 2.
That'd be 1.
It would be 1. So it's from the midline to the peak or the trough, not from, so it's half the distance from the bottom to the top. Everybody good so far?
Fantastic.
All right, turn the page.
Amplitude, so this is like the peak and then this is the trough, so the amplitude from like this to this, and this to this.
It's more if I drew a perpendicular line down from the peak to the trough to that midline, it's the distance of that line.
Oh, okay, I see.
This if I look at this as my starting point at 0, it's right in the middle of the curve. Okay?
I thought I was good, I'm not good.
All right. Now, we're not doing all of cosine.
Thank you.
So the amplitude would be 0.5 on that also?
No, the amplitude would be 1.
Oh,
I'm going to draw those same 4 points, right? So this is 0, 1. This is 1, 0. Hey, guys, if I asked you the cosine of a function on the unit circle, what do you give me?
X.
You give me the x-axis, yes? The x-coordinate. All right, so at 0, what's my x-coordinate? 1. So for cosine at x equals 0, y equals 1. And then if I travel pi over 2, I'm moving all the way to the top here. What's my x-coordinate? So what's the cosine of pi over 2? 0. Because it's just the x-coordinate, pi over 2. What's the cosine of pi? Cosine of 3 pi over 2.
0.
And then back up to 1. I'm just going to plot those points. Now, we're not going to write down all the in-betweens, you guys, but look at the numbers of the in-betweens. Do you see how they are the same numbers as when we did the y's? Like, because the x's and the y's on the unit circle are the same. So as we look at these points, these still have that same curved wave. Okay, because it's the same square root 3 over 2's in between and square root 2's and 1/2's. Okay, and if I go in the other direction, I'm kind of in the same place. So the cosine graph is also periodic. It repeats itself because the x-coordinates as we go around the circle will start to repeat themselves as well. Okay? All right, so looking at this, what's the period of this graph?
Y equals 1.
Remember, the period is the time it takes to repeat itself. So I'm gonna trace the graph, Just tell me when it starts repeating itself again. Just like we did last time. Cool? Now, okay. So are you guys good with saying that this graph repeats itself from here to here? That's like the distance it needs to not repeat itself. Okay? And that distance is 2 pi. I know that because it goes from 0 to 2 pi. So the period of this graph is, in fact, 2 pi. All right. Now the midline. The equilibrium, the halfway point between those peaks and that troughs is
Y equals 0.
y equals 0.
Are all the problems that you're going to give us have
No.
Why is it y equals 0?
Because to be on the x-axis, your y-coordinate has to equal 0. The other one was y equals 0 as well. It should have been. Amplitude. Amplitude goes from here to here. You can pick any peak to any trough, okay? Is 1. So when you look at these graphs, sine and cosine, how are they similar to each other? Well, the period for both of them was 2 pi, the midline was y equals 0, and the amplitude was 1. So here's my question. How are the two graphs different from each other?
The shape of them.
What do you mean the shape of them? They both have a wave shape, yeah?
Like the pattern of this one is more like a W, while the pattern of the other one is more like it goes up and then it goes down.
It's like inverted. Or like
Okay.
moved over by something.
Sine started at the bottom?
In the middle.
Well, yeah.
I like the way you said that. I really like the phrase started at, 'cause that's where I want you guys to think about this, okay? So sine starts at the midline. In other words, when x equals 0, sine starts on a maximum. And that's a pretty big deal. Sine starts at the minimum, or at the midline, cosine starts at the maximum. So, guys, everything we're going to be doing with these graphs is just being like, hey, I have something where equilibrium is 55 degrees. So how am I going to rewrite my equation so that it has a midline of 55 degrees? I have something that peaks and troughs should be higher and lower. So we're going to look at how do we transform the original equation to get different graphs. Finished up with yesterday. Cosine starts on a highest point. Sine starts at that equilibrium, cosine starts at its highest point.